Hi, welcome to this video on magnets and currents and examples of questions. On the first question that I wanted to have a look at, we have an electric circuit, as you can see, and they tell us that there is an electromagnet connected to the circuit. So here is the very rudimentary electromagnet. It's a iron core rod here, and then it's got a wire coil turning around it, and then here there's a switch, which is right now it's open, you can close or open, and here we have two batteries with the positive side this side. The big side is always the positive, so that's the way in which the conventional current would flow, which I mentioned before. A conventional current is really supposed to be positive current, but the direction in which the actual electrons go is in the opposite direction to that, so they would actually be flowing like this, even though the current, if we had to label this diagram, the conventional current, we would label like that, right? And that's because the big side, the long side of the battery, is on that side, and that means positive side. That's all a convention. Okay, so even the fact that electrons are negative, that's a convention, right? Somebody, when they invented electrons, they could have said that's positive charge, so it just matters that it's the opposite of negative, so all of that is a convention. But it's important to know that the positive side is this and the current flows in that side, even though that the actual charge flows in the other direction. Okay, having said all of that, the question is actually quite an easy one, this one. It says state two ways of making the strength of the electromagnet weaker. Okay, so two ways of making it weaker would be, first one would be to have here we have 1, 2, 3, 4, 5 turns on the coil, so we could have however many less turns on the coil. E.g., we could only have 3 turns, then we would have a weaker electromagnet, and conversely many more turns would make it stronger. And the second way would be to have a smaller current in the circuit. So instead of having 2 batteries, for example, if we only had 1 battery, then the voltage would be less, the EMF generated would be less, and therefore the current would be less, and then the electromagnet would be weaker. So a smaller current will also do it. Another way of making it weaker would be just to take away the iron core altogether and to just leave the coil, right? A coil in itself will behave as a magnet, a coil with current. One side will act as the north pole and the other side would act as the south pole. But if you put on an iron bar, a core here in the middle, then it amplifies the effect. I've talked about that in other videos, but that would be another way of making it smaller. So those two would be valid. So with the other one, part B of the same question says, explain why the core is made of iron and not steel. Steel is not really suitable for electromagnets because it's a hard magnetic material, it's a hard magnet. That means that after you magnetize it, it stays magnetized. And the whole point of an electromagnet is that you can control. So with an electromagnet you can control, you want to be able to turn it on and off, and steel would become permanently magnetized, so that would not be suitable. So steel would become permanently magnetized, so not suitable. Okay, so that's the first question, and that would be full marks there. Iron is a soft magnetic material, so the moment you turn off the current, whatever's making the ion magnetized, which has to do with the domains inside of the ion and the magnetic moment of the atoms in the ion, the current. The moment it goes away, then the effect is in the ion is lost. The orientation of the magnetic moments becomes again random, and so the electromagnet loses its property as a magnet, and so you can turn it on and off. So that's a very useful thing to be able to do, because you can trigger things when the magnet is working, or switch things off, etc. They're very useful in circuits. So the second question I wanted to have a look at is this. They give us certain blocks, and we don't know whether they are magnetic or not, and they give us different combinations of them. They give us, for example, they tell us, okay, if I put A next to B, then the effect is that there is an attraction. Then they tell us if I put material B next to C, then there is an attraction again. But if I put A next to C, then there is no effect. And if I put B next to D, there is no effect. Okay, so given us this, then they give us three options for labels on the materials A, B, C, and D, and the three options they give us are, it's either a magnet, or the label could be that it's a magnetic material, which is different from it being a magnet. I hope you a magnetic material. And the third label that we can have is a non-magnetic. Don't know what that says. Magnetic material. Okay, so these 4, A, B, and C, and D are either a magnetic material, or a non-magnetic material, and so we have to decide what they are. Now, so let's think this through. If A and B are attracted, then they either are both magnets, or one of them is a magnet and the other one is a magnetic material, right? So A and B are around here somewhere. I would put them around here. They're either magnets or magnetic materials. We're not very sure what they are going to be. B and C, similarly, if they are attracted, then they need to be also around here. So A or B, we already know that it's around here. So C, we can put it in here also, in this group of either magnets or magnetic materials. And now we have to decide if they go up or down. What about C and D? What about D that we have left here? Well, D only pops up here in this fourth group, and it interacts with B and has no effect whatsoever. So D is definitely gonna be, since there's no effect here at all, it cannot be a magnet. It could be a magnetic material, and then B could also be a magnetic material, without either one of them being a magnet. So let's put D here. Okay, and now let's see if it's possible for D to be a magnetic material. So before I talk a little bit about that, I need to first make sure that we all know what we're talking about. If I have a magnetic material here, like a lump of iron, that's a magnetic material, and if I have here another lump of iron, or a lump of steel, right? These are all magnetic materials, but since there's no magnetism in any of them, they haven't been magnetized or anything, then they can be next to each other, and there won't be an effect, there won't be an attraction or repulsion or anything like that, right? But if I now come along and I've made this steel, I've made it into a permanent magnet, imagine that's a north pole and that's a south pole, then that's going to induce here the opposite effect. So that would become a south and that would become a north, and then suddenly here we would have an attraction. Right, so a magnetic material with another magnetic material, you don't necessarily have an attraction, but a magnetic material next to a magnet will definitely have an attraction. So having said that, and one last thing, a non-magnetic material, obviously, like a piece of plastic or whatever, if you said here plastic, then it doesn't matter if you put it next to a magnet or next to a magnetic material, it won't have any attraction whatsoever, right? So a non-magnetic material won't be likely to be magnetized or anything like that. So hopefully that also makes sense. Let's see, so B appears in this first pair and there's an attraction, and B appears in the second pair and there's an attraction. So I'm gonna go ahead and assume that B is a magnet and then see whether everything else can be consistent around it. So let's put B in the magnet place. B also appears here in the last one and there's no effect whatsoever. So if B is a magnet, I've gotta then say that D is a non-magnetic material, because if it was a magnetic material then there would be an attraction. So if B is a magnet, D has to be a non-magnetic material. And what would that give us for the rest? Well, if B is a magnet and A and C have no effect between them, and A and B here there is an attraction, then let me say that A is a magnetic material. A is a magnetic material, and see if everything fits in together, okay? If A is a magnetic material, then A and B would have an attraction, that's correct. And then here A and C have no effect. If A and C have no effect, then C has two options. It can either be a non-magnetic material or it can be a magnetic material. But it's not going to be a non-magnetic material because here B and C interact and there's an attraction, right? So C has to be a magnetic material. Magnetic material. And now let's see if these make sense. B and D no effect, so that's magnet with non-magnetic material, that's fine. A and C no effect, so that is a magnetic material with a magnetic material. No effect, that's fine, because as I talked about before, a lump of iron next to another lump of iron, if neither is magnetized, you won't have an attraction, so that's fine. So we sorted, we definitely got this one right, we got that one right. B and C an attraction. Let's see, B is a magnet and C is a magnetic material, so yeah, between a magnetic material and a magnet there would be an attraction, so that's fine. And finally A and B attraction, A and B magnetic material and magnet, so that's fine also. So here we started with a little bit of an assumption and we said, okay, B seems to have cause attraction here and there, so let's call that a magnet. Then we looked down here and we said, okay, that's a magnet, that has to be a non-magnetic material because there's no effect. So I put that there, and then I just followed from there with a bit of logic, and we got the answer. All right. So hopefully that makes sense. And we'll go on to the next question, and that will have to be in the next video because it's a bit of a longish question, and although very useful, and we won't have time to finish it in this one. So I'll see you in the next video.